So, welcome back to this continuation of this course, and again I would like to welcome you back to the second session today on basic design methods. And as I said that I will constantly drive around the process, and I would request you also to not only try and imbibe, adapt the process, but also try to ingrain it within the students of your class about following the process. So, we have in the morning today seen a few examples of how to get the initial solution, and we have seen two of the schemes, one on balancing the split, which is actually optimizing the divide and conquer, which we do both by asymptotic analysis of the recurrence relation, and then we open up the recursion space to do it. We did the binary search problem, we did several versions of the sorting problem, the subarray problem, and then we went on to look at the other technique, which is that of when you examine the search space, you try to look for identical subproblems and try to memorize those, so that when you have to solve it again, you actually do not do it multiple times, you just remember that in the memory. A question that came during the discussion at that time was that of the iterative method. As I said, the iterative method will come in when we are finalizing the algorithm. I wanted to discuss that a little later, but since some doubts came into the class, so I thought that we will have a quick look at the whole process again. So, let us look at the process of trying to finalize the solution for the problems that we have done. So, let us first take the binary search problem that we have done, and in the binary search problem you will remember our approach was that we looked at the problem, the list L was given to us, search BSL, and we are looking for an element k. Obviously, if the size of L is equal to 1 and L1 is equal to k, we return true, and if L1 is not equal to k, we return false. This is the base condition. The recursive condition, if the size of L is greater than 1, then we split this L into two parts, L1 and L2, and choose one element, either the last element of L1 or the first element of L2. So, we choose some L and compare it with k. And based on comparison with k, we decide to search either of L1 or L2 with k, and which of the L1 by removal of L. Now, once we have this and we have decided that this split of L1 and L2 will be done exactly in the middle. So, our algorithm then becomes that we take the list L, we split it in the middle, and then we find one element from that middle of the list. So, we find one element from the middle of the list. So, we find one element from the middle of the list and compare with this element and then move this side or this side. The question that was asked, if we maintain it recursively, then what about this list as soon as it goes on in the recursion? This list obviously will go on and on in the recursion, and it may end up by requiring more space in the finalization of the algorithm. So, the natural answer to that is that if you would then like to maintain a global array A and just pass the indexes. So, that is how we reach the final version of this algorithm. It is still a recursive algorithm, as you can see here. you search the array A I to j with element x, and if I is less than j, that means you have your array, you have looked at all the elements. Otherwise, you choose an index q between the range I and j. We have decided that we will split it right in the middle, and then you search either from the left half or the right half. And once you have decided on this generic scheme and you have decided to split exactly in the middle. So, once you split exactly in the middle, then all you can do is to finalize this algorithm is you keep the array A or the list L global. On the other hand, when we come to the sorting problem, that is, we come to any of our sorting problems, and let us look at the merge sort problem. This is the merge sort problem, where we have to sort a list or a set list L S. Now, if the size of the list is 1, then we return S. Otherwise, we decided that we will break it up into the middle, because that leads us to order n log n complexity, and we sort S 1, we sort S 2, and then we merge R 1 and R 2. The result of sorting S 1 gives R 1, result of sorting S 2 gives R 2, and then we merge R 1 and R 2. Now, after doing this analysis, we know that the time complexity is order n log n. But what is the space complexity? The space complexity, obviously, if we are to maintain, as we are maintaining here, two sets R 1 and R 2, then along the whole recursion, the copies of the sizes of the lists will be maintained. Therefore, how can we save the space? How do we finalize the algorithm? Now, in order to do that, the best way is to now again open up the recursion tree. So, once you open up the recursion tree, let us say that we had 8 elements. We had 8 elements and we are splitting right in the middle. So, we have 4 here, 4 here, then 2 here, 2 here, again 2 and 2, and then 1 element each, which is the base condition. Now, if we apply a recursive algorithm, then the recursive algorithm will start here, then come here recursively, come here, do this, do this, do this merge, come here again, go back, do this merge, then do this merge, come here, then come down here and recursively compute it in this manner. So, it will do a depth first recursion the way we are trying to define it. Now, when it does a depth first recursion, then the size of that list is passed on in the parameter stack. So, while the time complexity is n log n, therefore, the space complexity will also start increasing. The space requirement here is going to be one list of size n, here it is going to be a one list of size n by 2, here it is going to be one list of size n by 4, and here of size 1. So, the total space requirement as we go from here to here completely will be n plus n by 2 plus n by 4 and so on, and if you sum up this series, then this series will tell you it is order of, it will be order of the series which is n plus n by 2 plus n by 4 plus so and so plus 1. This series you can find out what is the complexity, what will it be? N. So, this will be order of n. So, while you will need approximately double the amount of space, because this sum typically adds up to n. So, you will require double the amount of space if you want to do it this way. Then people will say, okay, I will not do it this way, I will maintain a global array A, and I will not use any additional array to do any other work. So, global array A, when I split in the middle, I just pass the array indices, which is fine. But when I have to merge two sorted lists, in place merge without additional array in order n time is a non-trivial problem. I will request you to try it yourself. Normally, whenever we do a merge, we use an additional array. We compare this element with this element, and then whichever is the larger we put into the second array, and we go on moving the merge algorithm that way. But try and do the merge algorithm within the same array, and you will see that you are having difficulties. Therefore, even in merge sort, even if you use a global array, and if you do not get order n merge, if you take anything more than order n, then the merge sort algorithm will never take order n log n time. Anything more than order n will drive the complexity of the algorithm that way. Therefore, this part of using a global array and not using any temporary array inside is again non-trivial problem. So, while everybody thinks that recursion stack goes up and down, it depends on the problem at hand. In this problem, it is not so easy for us not to use an additional array and do the in place merge. On the other hand, in quick sort, where you have to take a pivot element and then try to get a the rest of the array exchanged around the pivot element. If you can find the pivot element, then you can do that exchange in that same array itself. All of us know that there is the 2 pointer algorithm that we have, and we can just move the pointers through exchanges. But quicksort has the other interesting problem, that in quicksort finding the, see, if the pivot element is random, then it is easy. But if the pivot element is to be found as the median, then finding the median only with a single array is again another complex problem. Therefore, there is a very intricate and interesting nature of the time into space complexity. So, there is the time space joint complexity of a problem, and for sorting the joint time space complexity. So, time space complexity is not the only thing in physics. Physics does not have overall rights to time space complexity. In computer science also, we think that time and space complexity are unrelated, but they are not. And the sorting problem is the simplest example which will show you how to find it, which will make it really difficult for you to contemplate on how to do it. Next comes the question of iteration. Do we need to do it? Do we need to do merge sort only by recursion? So, how can we try and do merge sort just not by recursion, but also by iteration? So, that is a very interesting question. In order to look at any problem and try to solve it by an iterative approach, you must have a very good control over the recursion tree structure. And unless the recursion tree structure is well understood by you, you will not be able to get that in the picture. So, here if we look at this recursion tree structure, then if we want to iterate, in recursion we were doing it like this. I will just show you the sequence in recursion once more. We will go like this, then like this, then like this, then like this, then like this, like this. This is the sequence of recursion. On the other hand, if we want to look at it from an iterative point of view, then let us redraw that thing and we will see how it will look different. In iteration, we would rather do it in a different fashion. We would do this first, we will do this first, this second, this third and this fourth. Then we will do this fifth, this sixth and finally this. So, in order to do this, we will have one loop which will take 2 at a time and do it. So, in the array that we have the whole element, we still need an additional array for merging, but we will now take 2 at a time, these 2, then these 2, then these 2, then these 2 and so on, and get this iteration done. Then there will be an outer loop which after completing this iteration will go to this iteration. And in the inner loop now, the indexing will increase from doing 2 elements at a time to 4 elements at a time. And then in the outer loop will again go and again do this. Now, it will do 8 elements at a time. So, you will have this array and you will use an additional array to do whatever you want, because the in place merge is not possible in the same array, but still you will write an outer loop which will be for I equal to, it will start from the bottom, and how many steps in the outer loop will be there? The height of this tree. The height of this tree is how much? Log n. If there are n elements, then if there are n elements, if there are 8 elements here, then this height is 4, 1, 2, 3, 4, and the number of iterations that you have to do is 3. So, you will do an iteration from I equal to, you will find k, you will define as log n what? Ceiling minus 1, because if you had got 7 elements, still you would have had to do 3 iterations. Only if you have got how many elements? 4 elements will you require to do 2 iterations. So, for I equal to 1 to k will be your this outer loop. This is the outer loop, and then the inner loop will start from I equal to 2 for j equal to 2, that you will take elements 2 at a time, and it will go on in every loop. It will be increment of step. What will be the step? J equal to j into 2, because first it will do 2, then it will do 4, then it will do 8 and so on and so forth, and you have to do the indexing correctly, and here you will have to write the appropriate merge routine. So, the whole of the recursion that you are doing can be converted into an iterative process. So, but still here the space complexity, since you cannot do an in place merge, will require you to do a different sort of merging. So, there are times in which you can convert the recursion to iteration. Let us look at the Fibonacci problem. Let us look at the Fibonacci series problem. The Fibonacci series problem, which we had done a little while earlier, let me try and take out that piece of paper if I can get it. Yeah. This was our Fibonacci numbers problem, you remember. It is f fib n equal to 1 if n equal to 1 and so on, and it is plus. And we said that this is the full tree, and we wanted to solve the identical problems only once. And in order to do that, we can obviously say that if we collapse it like this, then the easiest thing is to start from bottom. You know f 1, you know f fib 2, then just start from 3 to n and just do an array computation and you will get the value. But suppose instead of Fibonacci, I give you another function. I tell you f nu is equal to 1 if n is less than equal to 5, is equal to 12 if n is greater than equal to 215, and is f nu n, sorry, n is equal to f nu n minus 6 plus f nu n plus 23 otherwise. Now you are in trouble. How will you start your iteration? Everything is same as the Fibonacci series, but in the Fibonacci series you had the advantage that you could actually, there was an order, f n only has dependencies less than n. Now you have greater, less, where will you start the iteration from? So, always, even if you have to memorize, the iterative process may not be feasible. For the standard Fibonacci series, the iterative process is easy. For the standard problem, you can always write this. Here we have taken different basis conditions. So, fib equal to 1. So, for the standard process, all you had to do was write fib val, take an array, fib val 1 is equal to 1, and let me just do it on the screen. Fib val 1 is equal to, so define an array fib val and initialize fib val 2 equal to 1, that is what we said in our definition, and then for I equal to 3 to n do fib val I is equal to fib val I minus 1 plus fib val I minus 2. That is all. But for a case like this, how are you going to write such an iteration? So, the only option that you have, and the option that has to be adopted, is that I will still maintain an array, and what I will do is I will maintain an array called fib val. And I will initialize all fib val values. I will maintain this array and I will initialize to some inapplicable value. Since we have used addition here and all numbers are only positive, therefore, no negative number can be there. So, for the time being we will initialize everything to minus 1. If we do not have an inapplicable value, then we have to use a separate array to identify whether that element was done or not done. So, otherwise, other than that, if otherwise we will use an array done, which we will all initialize to 0. And for the example that we have here, where we have two basis conditions, given these two basis conditions, it is easy for us to do. So, now we will write our new fib val the function that we will write given any n, we will now write a recursive function in such a way that we are always able to determine the value. So, what we will do is as follows. We will say if n is less than equal to 5, then the fib val array is going to be assigned to be 1. If n is greater than equal to 215, the fib val array n is going to be assigned to be 12. That was our definition. Otherwise, what we will do is, we will check if fib val n is not equal to minus 1, sorry, we have already called fib val n. So, we will check it for fib val, we have called it, we have asked it to be done for n minus 6 and n plus 23. So, we will check if fib val n minus 6, that array, is not equal to minus 1, then we will call new fib val n minus 6, and whatever answer we get, we call it y. Then we check if fib val n plus 23 is not equal to minus 1, then z is equal to new fib val n plus 23. Then what we do is, we now assign fib val n is equal to the array fib val n minus 6 plus fib val n plus 23. So, what has this done? If this value is not 1 minus 1, which means the value has been computed already, then we will use that value, we will not call the recursion. If this value is already computed, if it is not computed, then we will compute it. Okay. And during the computation, we will assign the value of this and we will return. This one also need not have been done. Yeah. So, this is if it is equal to minus 1, right? This should be equal to minus 1, I am sorry. If it is equal to minus 1, then you do not need to call the value. If it is equal to minus 1, then you need to call the recursion. If it is not equal to minus 1, then you just use the value. Now, what does that guarantee? Here is a case which we saw, where the iterative approach is not possible because of the nature of the recursion. You really do not know how you will iterate between a number which is greater than and less than n. You really do not have an obvious way of finding the iterative approach. But if you use global values and you assign them correctly, then even by the recursive approach, you will still ensure that you are not solving an identical subproblem more than once. You are memorizing the old values in a global array and you are able to solve the problem still in order n time. So, this is what you would do, and if you look at, so here where we have done is that if fib n is, there are other ways of writing it. So, if fib n is not is equal to minus 1, then you call it, otherwise you just return the value of what it is. I did it by a different method, here it is a little easier way of writing it. You check the value of the array, if the value of the array is already done with the appropriate value, that means the problem has been solved before, you just do it once, otherwise you call the recursion. So, the other very interesting so in terms of divide and conquer, there are two other interesting problems which we have discussed in our lectures. One of them is the multiplication of two n bit numbers. The problem statement is as follows. You have two n bit numbers which are bit numbers. So, they are all 1 0 1 0. They are all 1 0 1 0 type of. And how are we going to multiply them? We know the longhand multiplication. And I would request you to watch the video and the slides of the original lectures, because there we have explained this in great details. And it is very interesting to see that I can apply a divide and conquer approach. I can break this into two parts. So, if this was A and this was B, I can break this into two parts, A1 and A2, and B into B1 and B2, and I can write down the multiplication of this in terms of multiply and shift. For example, it will be A2 B2 plus A1 B2 into 2 to the power n by 2 shifted, plus A2 B1 into 2 to the power n by 2 plus A1 B1 into 2 to the power n, and 2 to the power bitwise n is just shift. So, I can write it this way, but even if I write it this way, it becomes, if you look at it, I had to multiply two n bit numbers. Now, I am multiplying 4 times, I am multiplying n by 2 bit numbers. So, for T n, I end up with 4 T n by 2 plus order of what? This is multiplication and shift. So, shift is order n. So, this will eventually still turn out to be order n squared. This is n on n squared. This is n on n squared. If you have to multiply two n bit numbers, then this is what we have written here, and this requires 4 such multiplications, and with 4 such multiplications you reach this. And if you apply the master theorem for this, if this was 2, then it would have ended up with n log n. But this being 4, this ends up with order n squared. It does not help you at all. On the other hand, this is not balancing, but this is a different way of doing this multiplication. So, if we, instead of doing it in this longhand way, if we use this P1 equal to this, P2 equal to this and P3 equal to this, then we can rewrite this whole computation in this form. It is a little tricky, but once you look at it, you will see if I do it in this form, then I end up doing actually 3 multiplications, one here and one with this and this. And I require some more additions, which is fine. Additions and shifts take all order n time. Then my complexity becomes T n is equal to 3 T n by 2 plus order n. And the difference, but this being this and this being this, completely transforms my complexity. This completely transforms my complexity. So, previously it was 4, and now instead of 4, we can do it by 3 multiplications and some more additions, but that does not add to this. So, this now the complexity changes to n log 3 to the base 2. This actually was order n log 4 to the base 2, which is order n squared, but log 3 to the base 2 is much less than n squared, and this leads to an order of 1.83, not 1.83, some 0. 1.8 or something, 1.8 or 1.7, I do not remember the exact value, 1.5 it says. So, it is about 1.58, which means that here is another approach where the divide and conquer itself and the use of the master theorem will help you to get it done. Again, once you get this done, you have to decide on the final algorithm, and the final algorithm, to do the final algorithm, you have to see whether you can convert the recursion to iteration. To convert the recursion to iteration, you need to understand the structure of that recursion very well, and if you can, then it will work out, but if you can't, then it will not. Another non-trivial problem in the problem domain of dynamic programming, there are several such problems. One of them is the classical matrix chain multiplication problem. The matrix chain multiplication problem is a series of matrices which have to be multiplied, and the sequence in which you multiply the matrices determines the number of multiplications that you have to do. And therefore, finding the optimal sequence for multiplication is an interesting and important problem. If you go through the lectures, the textbooks and others, this is a very classic problem, and you can show that this is created out of this recurrence equation. Mij, multiplying matrices from M, so there are matrices M1 to Mj. So, for M1 to Mn is the set of matrices, and if I have to multiply Mi to Mj, then the optimal cost of multiplying Mi to Ij is 0 if I equal to j. Otherwise, you look at all options Mik to Mk plus 1 j and the addition things to multiply them, and you look at all options for varying k from I to j minus 1, and among them you will take the minimum. So, this is the problem as such, and once you open up this recursion tree, you will see that there is a whole world of identical subproblems coming up. So, in order to solve these identical subproblems only once, all we have to do is to be able to memorize this Mij values, so that whenever it is done once, it is done and you will retrieve it next time you get it. But if it is not done, then you will do it again. So, using the same recurrence equation, you can directly convert it to a top down definition. This is there in the slides which is there with you, and again you will remember an array done Ij. If it is done, it is non-zero, and if it is not done, it is 0. So, if done Ij is 0, then you run the evaluation, otherwise you just pick up the value from the array, and the whole evaluation works on the recursive definition. Only you check whether it is done or not. If it is done, you retrieve the value, otherwise you call the function, and at the end of the function, when the function is computed, you assign done equal to 1 and you store the result in the value. So, by this top down mechanism, you can always ensure that you will get it done only once. Now, if you open up this recursion very carefully, then you will see that there is a structure. So, if you open up this recursion very carefully, you will see that there is a structure, and all classical textbooks show you that structure. The structure is that I and j are continuously increasing. You have got Mij and then you do it half. So, you can build up a 2-dimensional array of Mi and j and start by doing all the diagonal elements first. All the Mii's you do, they are all 0. Then you do all Mij's such that their distances are 1. Then you do all Mij's such that their distances are 2, that is j minus I is 2. Then you do 3, then you do 4, then you do 5. So, once you can define that structure, then you can convert this recursion to an iteration. On the other hand, if the recursion was very complex and you could not evolve this structure, I showed a very simple example in the Fibonacci series, then you would left to do with this top down approach itself which we showed. So, the top down approach will work, and it may take some additional memory in the recursion stack, but if you maintain the global values separately, then there is only small additional memory that you will require, and otherwise if you can get the structure, then you can convert it to iteration. Now, we come to another area of problem solving. So, here is the iterative solution for this problem. As we said, the differences will start from I to j minus 1. So, the whole difference will be 1 1 1 1. So, here you have assigned all the i's to 0 and then you go on doing. You can have a look at the textbook to do this. Now, let us come to another problem. Let us come to a new problem. It is actually an old problem. I am trying to fool everybody by trying to tell that it is a new problem, but it is not a new problem actually. So, it is called the robber's dilemma problem. I am sorry. So, we are now trying to define so in this problem a thief has now entered a museum. So, a thief has managed to enter our reserve bank where all the gold coins are kept. So, there is a huge bag of gold coins kept and the thief has got into taken a suitcase and taken this with him. And once he enters into that, he thought that there were only gold coins, but he sees that there are gold coins, there are platinum coins, then there is diamond dust and there are several other things available there. And he has only one suitcase. Now, in this suitcase, this fellow wants to make the maximum killing. So, he has to decide what to take and what to leave behind. So, bechara what he has done, he doesn't know what to do. He has attended PP Chakravarti's algorithms class. So, he sits down there, takes out a piece of paper and starts writing a recursive definition. So, he has now realized he has got the whole night to steal this. So, what will he do? So, first thing he has said that he starts to remember, then he forgets what he has to remember. So, he takes out his mobile phone with the video recording of the class, and in the video recording of the class he is told that first he has to specify the problem. So, he takes out his piece of paper, leaves the bag aside, looks at all the material that is available and starts specifying the problem. So, how does he specify the problem? He is told that he has to make input. So, in the input he finds that there are items. So, there are items I1, I2. Imagine what has happened to him. Firstly, he was a computer science student, then he lost his job and became a thief. And now he is back. If he had studied this carefully, he wouldn't have had lost his job. So, he finds that there are n items. Then, for each item, he finds out what is the value of that item. Because they are all small items, he can just take it like this and put it in his bag. He can take it in his hands and put it in his bag. So, he looks at the items. So, then he finds the value of these items per kg. What is the value of these items per kg? Okay. So, for each item there is a value and there is how many kgs of that item is there. So, he has the values of these items V1, V2, V3 up to Vn. This is the value per kg. He wants to take all the items, but his problem is that his bag can take only B kg total. And each item has got a total weight of what it can, what is there. So, no item is of b kgs, it is but a big bag, no item is of b kgs. So, what will he do? He will have to choose which item to take. So, then he starts thinking what to do. So, his final choice is how many kgs of which item he will take. How many kgs of which item he will take, so that his total value is maximized. So, after having determined the value, that he knows that platinum is this much value, gold is this much value, silver is this much value, diamond dust is this much value, etc., etc. Now, this fellow has to now determine what he will do. So, next he sits down scratching his head to find the recursive definition. So, in the treasury he is sitting there trying to define what he will do with each item. How will he get the recursive definition of each item? So, he starts his process and he says, I will select from the list of n items. He wants to select which item and how much. So, he has to first select whether he will take an item and how much of that item this fellow will take. So, there is enough of that item or less of that item he will take. So, first he wants to select which items to take and what is the value of that item. So, for each item I have got total weight W1, W2 up to Wn. If I take an item, I can choose how much of this item I will take. And now, he has to write down this recursive definition. So, in this recursive definition, for every item, he will have to decide on two things: how much of the weight he will take of that item. He can take any weight value between 0 to W1. He can take any weight value between 0 to W1. Okay. So, he will have to decide that in order to select n items of a total capacity B, for any items he will take the first item. So, there is the list of items I1 to In. So, he chooses the first item and he has got the following choices. He can take any value between 0 to W1. So, then he starts thinking what he will do with this item. So, he starts planning and says that is there a way for me to choose an item V1, whether I will take, how much should I take? Should I take the full value? Should I take 1 unit, 2 units, 3 units? So, he can choose an item and he can choose an item. Suppose he chooses 1 unit, then B becomes B minus 1 kg. So, he can choose one of them, 1 unit, or he can choose 2 units and so on, up to select n minus 1 B minus Wi. And why did I put n minus 1? Because when I put it n minus 1, so this is, he has chosen item number 1. Now, when I go to n minus 1, he will choose item number 2, then he will choose item number 3, he will choose item number 4, he will choose item number 5, and so on and so forth. Now, if he selects this item, then we must know what this is what. So, how much weight is going down in his sack, but he also wants to evaluate how much is the profit obtained. So, this function must return the profit obtained. This function must return the profit obtained, and what he wants to do is to select the one with maximum profit. He wants to select that one with maximum profit. So, I have not written the basis conditions. I am asking you to think about now, if you were the robber, then what would you do whole night, whether you would be able to write the recursive definition or not. And once you are able to evaluate this, then if you have read the algorithms design course, then it will become very easy for you. Why? Because you will realize that if you sort the items in terms of its value per weight, per unit weight, and you choose the items instead of choosing them, I will take so much of this, so much of that, so much of this, you choose the items in order of their value per unit weight, then your profit will be maximized. You first you find out the item which has got maximum value per unit weight, you take as much of it as possible. Then you take the next item with maximum unit value per unit weight, you take as much of it as possible till you fill up the sack, or you till fill up your bag, and then run away. So, you are not only greedy, you also know the greedy algorithm. So, if you are both greedy and you know the greedy algorithm, then you can run away with everything with maximum value. Otherwise, if you are greedy and do not know the greedy algorithm, then you will take something and run away. And if you are not greedy and you do not know the greedy algorithm, both of them you do not know, then whole morning you will be computing till morning and you will get caught with nothing left for you. So, this robber's dilemma is actually a variation of what is called the knapsack problem. In the knapsack problem, you are given a set of items, each item has got a profit and each item has got a weight, and there is the knapsack to be filled. And in order to solve the knapsack problem, you can write the recursive definition. And by the way, if you had attended the class and if you knew it was the knapsack problem, then you would have written the definition in very quickly. So, the knapsack problem, let us go and now try to work it out. On the knapsack problem would be that you have got a set of n items. Each item has got a profit P 1, P 2, P n, and each item has got a weight W 1, and you can either take this item or not take this item, that is one approach, or the other is you can take part of the item, or you can take part of the item. If you can take part of the item, then you have a greedy approach. On the other hand, if you are told that you can take the whole item or not take it, then there is no greedy approach for that. In that case, it is called the 0-1 knapsack problem. So, the knapsack problem, for this you can write down the recursive definition you can write down the recursive definition of the knapsack problem as you start from item 1 to n. So, you start from any item I, your total sack capacity till now is S and your total profit is P. And then if I is equal to n, then you return P, that you return, you have chosen all the elements. Otherwise, you take the item I and decide whether you will choose the item or not choose the item. So, one option is you will choose the item and go to I plus 1. If you choose the item, then it is S plus Wi, P plus Pi, sorry, S minus Wi and P plus Pi. These are all small p's. And if you do not choose the item, then it is I plus 1, S and P. And whatever you get out of these two, you want to take the maximum. There are other cases, corner cases that you have to consider. If this is equal to 0, if S is less than 0 and is equal to P if S is equal to 0. And this recursive condition is if S is greater than 0. You will go on doing this only if S is greater than 0 and I is less than equal to n, and you start with 1. So, you can choose this or this. This is the branching. So, you will get a branching, a binary branching on using the inclusion or exclusion principle. Here you choose the item I and here you do not choose the item I. And this is how you develop the initial recursive definition. So, if you are told that you can either choose or not choose the item I, then you cannot apply the greedy approach, you have to solve both sides. That comes from a different nature of the problem which we will discuss when we discuss NP completeness, because this problem, the 0-1 knapsack problem, is a hard problem. It cannot be solved in polynomial time, at least not known. On the other hand, if you can take any part of the item, then you can show that this I plus 1, I plus 2, the way we are doing it, could be ordered. It could be ordered and you would order the items in terms of their Pi by Wi ratio, which is the profit per unit weight. And instead of choosing this side or that side, you first sort it by the Pi by Wi ratio, and once you sort it by the Pi by Wi ratio, all you need to do is go on taking the elements till the knapsack becomes full, because you can take any amount, and since you can take any amount, you can fill it to its full capacity. So, from the same definition, the analysis of the problem and slight variations of the problem will actually lead you to whether you will apply the greedy algorithm or whether you will apply the recursive algorithm. Both sides of the recursion are required. The greedy tells you that in the recursion, I can irrevocably choose a particular path. The greedy tells you that in the recursion, I can irrevocably choose a path. Here, I had a chance of taking or not taking. So, I would have to either take or not take the element. On the other hand, if you could take any number and you know that I can do the greedy one, I will sort it and I will continuously decide to take an element in a particular category till it is over. So, the branching which was a binary branching two-way, you can irrevocably choose which one to take. The same applies for that spanning tree problem. I have discussed this in great details in the earlier lecture of the spanning tree problem, where we built up the recursive definition and showed that instead of taking any edge which goes, if you remember the spanning tree problem, you start with a particular node and then you look at edges which go out from this node to all the other nodes. And then obviously, you could choose this edge or this edge or this edge and pick up another node. And then from this set of nodes again you look at the remaining set of edges to the outgoing node and you can pick this. Normally, the recursive definition, as we have discussed in that class and you can see it in more details, would be to choose all of them and find the overall minimum. But you have that famous theorem which says that if you choose the minimum edge, outgoing edge from this set to this set, then that guarantees that it will be the minimum of all. So, here again that multiple branching could be greedily chosen into a single point. So, here what I am trying to stress is that again an analysis of the recursive definition will tell you whether you can make a greedy irrevocable choice or not. If you can make a greedy irrevocable choice, then that multiple branchings will drastically reduce to a single line and you will get the algorithm. That is how you can easily derive both the Kruskal's algorithm or the Prim's algorithm or the greedy knapsack algorithm when it will work, etc., etc. Now, if the greedy algorithm does not work, then again for such optimization problems, you will now have to do both the branches, all the branches and take the minimum or maximum as it applies. So, if we come back to the knapsack problem here, the knapsack problem as we have defined it here, knapsack ISP, there are three basis conditions. If I is equal to n, return P. If S is less than 0, return 0. Sorry, actually if S is less than 0, return minus, you return nothing, 0. Otherwise, you return P if S is equal to 0. That is, you have filled up the full capacity of the sack. Otherwise, you have to branch in two directions. That means, you initially had elements say x 1, x 2, x 3 up to x n, and you had a capacity C and you had an initial profit 0. Then if you choose x 1, then you are left with x 2, x 3 dot dot x n. Your capacity becomes C minus W 1 and your profit becomes whatever was your profit here initialized to 0, P plus P 1. And this side you are again left with x 2, x 3 up to x n, and here it remains C and P. So, this is chose x 1, not choose x 1, and you will build up this tree like this, and you are looking for that path to a leaf node. A leaf node occurs when either you have covered all the elements or the sack is fully filled. So, either you have covered all the elements and the sack is not full, or the sack is full, and you reach a value 0 if the sack is negative cost. That is, you have overloaded the sack with elements. If you are a robber, you have overloaded, the sack will break and you will have to go away empty handed anyway. So, once you have this approach, now you have to traverse this recursion. This traversal of this recursion now can be done in various ways. It can be done in a depth first manner, it can be done in a breadth first manner, etc., etc. Along with doing this in a depth first or a breadth first manner comes what is called the pruning condition. So, while doing this search, you have reached one solution here. This solution has given you a profit of P x 1. Now, when you are in another node and you have reached another solution, it gives you a profit P x 2. And if P x 2 is greater than P x 1, then you will choose P x 2, because you are maximizing your profit. So, during this depth first search, at any point in time at a particular node, you initially have 0 profit, but you will have what is called the current best profit available, stored by this mechanism. Whenever you reach a new solution, whatever is the better one you choose. And finally, if you search this whole tree, you will get the final best profit. Now, let us see at an intermediate node, your current best profit is C p, which has been obtained from somewhere. And at this node, you are at some jth point. That means, you have to choose elements from j downwards. And your current and your profit at this node is till now is P. And your remaining sack capacity is C. This is your remaining sack capacity and your profit is P. And you have these remaining elements left. Now, suppose we do a particular trick. We assume that I can take as many elements of any size I want. So, I apply the greedy algorithm to fill up the sack fully. That means, I choose the remaining elements in order of P by W ratio, and I go on choosing the most densely valued elements, and I go on and I take it right to fill up the sack, even if I have to take half an element, which I am not allowed. But by that, what I am doing is, I am trying to find out what is the additional profit that I can make, the maximum additional profit that I can make. That means, I greedily choose the maximum density element, and whatever little gap is left at the end, for that also I choose the element by cutting it, which I am not allowed. But if I do that, then I can show that this will be an upper bound on the remaining profit that I can make. And at this point, when I add P plus A p, if P plus A p is less than or equal to C p, so at this point in time at this node, my current best solution over all solutions is C p. At this node, my current profit up to j minus 1 elements is P. My current remaining capacity is C. I find an upper bound A p, which says after this I can get at most so much of profit. I add P and A p. If P plus A p is less than equal to C p, then I do not need to go down. This is called pruning. This P plus A p is called the bound, and this method of pruning, where we branch out, keep the current best solution and apply a pruning condition based on a bound at every node, is called the branch and bound method. If you look at our other video lectures, you will see we have discussed a problem called the stamps problem. The stamps problem is also a variation of the uncle auntie type of problem of the knapsack problem. and we will discuss this uncle auntie problem later on when we discuss NP completeness. They are all of the same family. So, they all have the same properties, DNA type, similar DNA in computational complexity. So, the branch and bound method is also a recursive, from a recursive definition, the way you traverse the tree, the way you bound the problem and the way you do pruning is the branch and bound method. There are other branch and bound methods, very sophisticated branch and bound methods called the best first branch and bound, which in artificial intelligence is called the algorithm A star. If you analyze, and I will not do it in details, if you analyze the shortest path problem in a graph, then the shortest path problem in a graph is actually you can derive that whole Dijkstra's algorithm by applying a recursive definition and then applying dynamic programming and applying branch and bound. And if you look at all of them together, and I will leave it for you to think about it for some time, about how you can derive the Dijkstra's shortest path algorithm by taking it from the recursive definition right till the end. While it takes a lot of time for us to understand and derive the algorithm, Edgar Dijkstra, one of the doyens of computer science, the legend is that he was asked, he says, yes, when somebody gave me to solve the problem, it took me 15 minutes to solve the problem. So, it took me about 20 minutes to write the first recursive definition. So, I am wondering what processor speed he has. The last point that I would like to make is that when you teach these algorithms, you also remember that these algorithms have the way in which we are doing it from recursive definitions has got a unique method, because it is not only amenable to single processors, it is also amenable to multiple processors. For example, take the maximum of n numbers. I am to find the largest of n numbers. We can see, and we have seen before, that we can split anywhere 1n, 2n, half, all of them will give us the correct solution of order n complexity to find the maximum of n numbers. But suppose I tell you I will give you unlimited number of processors, then how will you find the maximum of n numbers? So, again when we go back to the recursive definition, you will see that if I had 8 numbers, I could have done it by 2, 6, 1, 5, 3, 2, 2, 1, 1, 2 is the base condition because you can compare 2 elements, or even if I take 1, 1 as the base condition, I could do it this way. Here the total, if there was only one processor, total computation time is the number of internal nodes, which is n minus 1. On the other hand, if I did it this way, for a single processor, both would take same amount of time. But if I had given you 300 processors, then for these 8 elements in parallel, you would have compared all of them at the same time, then all of them at the same time, and this. You would have done it in 3 steps. But if I did this one, then I would have to do this in 1 step. Maybe these 2 I can do in 1 step, because they are not dependent on each other. But then this would require the 2nd step, this would require the 3rd step, this would require the 4th step, and this would require a 5th step. So, while the recursive definition for sequential, you could choose this one, because this leads to a very easy algorithm. But when you have to do a parallel algorithm, then the choice of which one of the split would differ. But it could still be derived from that same recursive definition. So, that is what is the idea, that you can also tell the students in the beginning class that this definition is not only meant for a sequential problem, but through this whole process even the parallel algorithms and other algorithms can be derived. So, in conclusion, there is only one thing that you will remember out of this course, that here is the process that we are trying to build, that you build an initial solution, you analyze it, and then the traversal of this recursion solution. From the opening up, you will know whether to do it by recursion or iteration, and once you optimize it, then your memorization is one thing, and then if it is an optimization problem, then pruning conditions will come, and the same process when applied, you will show that you will be able to see that almost all of them can be derived from the same process. So, this is the approach. The best way is to try and do it through examples and imbibe each one of them your own scheme to do it. And if we have a bunch of well defined case studies, if we develop a bunch of well defined case studies, I think it will be a very good contribution for us to do. So, my intention is to have a look at this, not to get disgusted by the way in which I ask you to do recursive definitions. Remember, there are greedy algorithms for which you can make lot of profit, and by this, if we can actually try and derive new algorithms, look at new problems or look at old problems and derive them and show that we reach this, as this 7,000 teachers of this whole program, if we are able to start solving even 7,000 problems, each one of them does one problem, and we are able to solve 7,000 problems in this method, we will be making an enormous contribution in terms of case studies of how the method can be used. So, I would request you not to get put off by the method, try it on your own, and in any way you have to learn the method, because day after tomorrow there is an exam. So, I think, so now we are ready to take questions. We will break for 5 minutes and then we will come back to take questions.